There's a sight in our solar system so iconic, so breathtakingly beautiful, it feels almost like a symbol of the cosmos itself. When you look at Saturn through a telescope, you aren't just seeing a planet, you're witnessing a celestial masterpiece. Those vast, gleaming rings, suspended in the blackness of space, have captivated astronomers and dreamers for centuries. They are a picture of perfect, serene order from a distance, a delicate crown around a gas giant. But what if that serene beauty is just the surface? What if, hidden within those brilliant bands of ice and rock, are secrets so profound they could rewrite the textbooks of science? We've long admired Saturn's rings for their beauty, but we're only just beginning to understand that they are also one of the most enigmatic structures we have ever observed. They are a cosmic puzzle box, and we are only now finding the keys. For generations, we viewed these rings as a beautiful but relatively simple disk of orbiting material. Yet every new mission, every closer look, has peeled back a layer to reveal not simplicity but staggering complexity. The closer we get, the more questions we have. These are not just inert bands of frozen debris, they are a dynamic, chaotic, and almost impossibly active environment. Forces are at work here that we struggle to explain with our current understanding of physics. Structures form and disappear. Particles behave in ways that defy prediction. There are gaps, waves, and patterns that hint at influences we can't yet see, gravitational dances with unseen moons, and perhaps even conditions that challenge our very definitions of what it means for a place to be alive. The rings are not a static photograph, they are a living, breathing movie, and we've only seen the first few scenes. Today, we are going on a journey deep into the heart of this mystery. We are going to explore not one, not five, but 25 profound mysteries hidden within Saturn's rings. These are not minor curiosities. These are fundamental challenges to our knowledge of planetary formation, orbital mechanics, and the very fabric of our solar system. We will investigate the bizarre physics that allows miniature moons to sculpt clean gaps, the perplexing spokes that appear and vanish like cosmic ghosts, and the tantalizing evidence that suggests some of Saturn's icy moons, moons whose material is continually recycled through these very rings, could possess environments capable of harboring life. This is a story of how a thing of beauty became a frontier of discovery, a place where every answer leads to two new questions, and where the next great discovery about our universe might be hiding in plain sight, waiting for us to finally see it. Our first mystery forces us to reconsider everything we thought we knew about the age of our solar system's most famous features. From our vantage point, Saturn's rings are brilliantly bright, reflecting sunlight with a stunning intensity that suggests they are made of almost pure, clean water ice. If they were billions of years old as Saturn itself, you would expect them to be much darker. Over immense timescales, they should have been constantly bombarded by a steady rain of dark, dusty meteoroids from the depths of space. This cosmic pollution would have gradually coated the icy particles, dimming their shine and turning them a murky brown, much like the dirty snow you see piled up on a city street at the end of winter. Yet they remain spectacularly pristine, a fact that points to a startling possibility. Saturn's magnificent rings might not be ancient. They could be a surprisingly recent addition to the solar system, perhaps forming a mere 100 million years ago. To put that in perspective, that's a time when dinosaurs still roamed the Earth. This means Saturn, for the vast majority of its long history, may have been a ringless planet, and we are just fortunate enough to be living in the brief cosmic window where its jewelry is on display. The Cassini spacecraft provided crucial data that deepened this mystery. By carefully measuring the gravitational pull of the rings on the spacecraft, scientists were able to finally weigh them. The results were far lighter than many had predicted. The entire vast ring system, stretching hundreds of thousands of kilometers across, may have a total mass equivalent to a modest-sized icy moon. This low mass is a key piece of the puzzle. A more massive ring system would better withstand the constant darkening process, its greater volume of clean ice diluting the incoming dust. A lighter, flimsier ring is far more susceptible to being quickly polluted and darkened. The very lightness of the rings supports the idea that they are not ancient, durable structures, but rather a more recent and perhaps more fragile phenomenon. Adding to the evidence is a process Cassini directly detected called ring rain. It turns out the rings aren't just passively collecting dark material, they are actively losing their own material to the planet below. Microscopic icy particles charged by solar radiation and dragged by Saturn's powerful magnetic field are steadily falling out of the rings and into the planet's upper atmosphere. This process is acting like a cosmic hourglass, slowly but surely draining the rings themselves. If this has been happening for 4 billion years, the rings as we know them would have largely disappeared by now. The fact that they are still here and still so bright suggests this draining process hasn't been going on for very long in cosmic terms. All these threads, the brilliant reflectivity, the surprisingly low mass, and the constant erosion, weave together to form a compelling, if controversial, theory. We are not looking at a permanent fixture of the solar system. We might be witnessing a spectacular but temporary celestial event, a fleeting masterpiece that graced the solar system long after the planets formed and that will, in another 100 million years, likely be gone. This realization transforms Saturn from a static icon into a dynamic, evolving world, and it makes our opportunity to see it all the more precious. This leads us directly to our second and perhaps most fundamental mystery. If the rings are not ancient, then where in the cosmos did they come from? Their very existence demands an origin story, a dramatic event that scattered countless tons of ice and rock into that perfect, balanced orbit around the planet. Scientists have proposed several grand, almost cinematic theories, but each one comes with its own set of compelling problems that leave the question wide open. The most long-standing and dramatic hypothesis is the catastrophic destruction of a moon. Picture this, a former moon of Saturn, perhaps a large, icy body similar to Titan or Enceladus, finds its orbit destabilized over millions of years by the complex gravitational tug of war with its sibling moons. It spirals inward, crossing a critical boundary known as the Roche limit. This is the point where the planet's tidal gravitational forces become stronger than the moon's own gravity holding it together. As it passes this limit, the moon is literally torn asunder. It wouldn't be a single explosive impact, but a gradual, inexorable stretching and pulling until the entire world is shredded into a cloud of debris. This debris, still following the general path of the moon's original orbit, would then quickly spread out to form the rings we see today. It's a compelling narrative of cosmic violence, but it faces a major hurdle: composition. The rings are almost 98% pure water ice, but we believe most of Saturn's moons are a mixture of rock and ice. For this theory to work, the destroyed moon would have had to be almost entirely made of water ice, which seems geologically unusual. Where would such a pure, icy moon have come from? An alternative theory suggests a more foreign intruder was responsible. Instead of a native moon, perhaps a large, icy comet from the distant Kuiper belt was captured by Saturn's immense gravity and suffered the same fate, being torn apart inside the Roche limit. Because comets are often far icier than moons, this could neatly explain the ring's stunning purity. However, the mechanics of this are incredibly difficult to model. For a comet to be captured rather than simply whipping around Saturn in a slingshot maneuver requires a very precise set of conditions, a cosmic ballet so perfect it seems statistically unlikely. It's like trying to thread a needle from 1,000 miles away while both the needle and the thread are moving at thousands of miles per hour. A third, more gradualist idea posits that the rings are simply left over from the original cloud of gas and dust that formed Saturn itself. In this scenario, they are primordial, a relic of the planet's birth. But this runs headlong into the age mystery we just discussed. If they were 4.5 billion years old, they should be dark and massive, not bright and lightweight. The evidence for youth seems to directly contradict this ancient origin. So where does this leave us? We have a violent moon destruction that doesn't quite match the composition, a statistically tricky comet capture that fits the composition but seems unlikely, and a primordial theory that clashes with the apparent age. It's a classic scientific puzzle where no single piece fits perfectly. Future missions will need to be our detectives, armed with more sophisticated instruments. They will analyze the chemical fingerprints of the ring particles with even greater precision, looking for traces of minerals or isotopes that could point definitively to a lunar or cometary source. They will map the ring's structure in unprecedented detail, searching for subtle density patterns or orbital quirks that are the gravitational fossils of the original catastrophic event. The answer is still out there, hidden within the icy grains themselves, waiting to tell us the story of their dramatic birth. But if the ring's youth is a surprise, their very substance is an even greater puzzle. This brings us to our third mystery, the composition conundrum. When the Cassini spacecraft analyzed the rings with its infrared and cosmic dust analyzers, it revealed a truth that was as beautiful as it was baffling. The rings are not just icy, they are almost impossibly pure. They are composed of about 98% water ice, with only a tiny, trace amount of rocky or carbon-based material mixed in. Think of them not as dirty snowballs, but as trillions upon trillions of perfectly clean, brilliant snowflakes, all orbiting in unison. This level of purity is something we simply did not expect to find in the harsh environment of deep space. The problem is that the solar system is a dusty, messy place. For billions of years, a constant, gentle rain of micrometeoroids, tiny particles of rock and metal from asteroids and comets, has been falling into the Saturnian system. This is cosmic pollution, and it should have coated the ring particles, darkening them significantly over time. It's like a white car parked outside. After a few years, it won't stay white without a wash. The rings, according to our old models, should be that dirty car. The fact that they are still gleaming white means something must be actively keeping them clean, or they simply haven't been parked there long enough to get dirty. This purity is one of the strongest pillars supporting the theory of a recent origin. But even if the rings are young, the near-total absence of rock is still a head-scratcher that demands an explanation. This leads scientists to propose some fascinating and unexpected cleansing mechanisms. One compelling idea involves a process of constant recycling and refreshment. The ring particles are continually colliding with each other, sticking together and then breaking apart. When they stick, they may form loose, porous clumps. When a micrometeoroid hits one of these fragile clumps, it doesn't just leave a dark spot. It can actually blast the clump apart, exposing fresh, pristine ice from the interior. The dark contaminant itself might be vaporized by the impact's energy or ejected away from the ring system entirely. In this view, the rings are a self-cleaning system, where continuous demolition and reconstruction are constantly scrubbing the surfaces clean. Another, more speculative, theory points to Saturn's powerful magnetic field. The icy particles in the rings can become electrically charged by solar ultraviolet radiation. Once charged, they become susceptible to the planet's magnetic forces. It's possible that this electromagnetic environment actively sorts the particles, somehow segregating the pure ice from the rocky dust and even expelling the contaminating material out of the ring plane altogether. This would be a far more active and organized purification process than simple collisions, but the precise physics of how it might work remains one of the ring system's many unsolved riddles. The breathtaking purity of Saturn's rings, therefore, is not just a static fact. It is a dynamic clue pointing toward either a very recent and violent birth that provided only clean ice, or to ongoing, hidden processes within the rings that we are only beginning to glimpse. Now, as we venture deeper into this realm of orbital dynamics, we encounter a phenomenon so elegant it seems almost designed the existence of celestial architects known as shepherd moons. These are not the giant, world-like moons of Saturn, but rather tiny, odd-shaped objects that nestle within the ring system itself. Their role is as precise as their forms are bizarre. Through their subtle but persistent gravity, they sculpt and maintain the very architecture of the rings, carving out pristine gaps and sharpening edges that would otherwise blur into chaos. It's a delicate, perpetual dance between creation and destruction, where these miniature worlds act as the master weavers of Saturn's most stunning features. Consider the Keeler Gap, a narrow, dark channel that runs through the outer part of the brilliant ring. From a distance, it looks like a perfectly drawn line in the ice. For years, astronomers theorized that a small, unseen moon must be orbiting within this emptiness, its gravity clearing a path by either absorbing or flinging out any ring particle that dared to wander too close. Then the Cassini spacecraft confirmed it, revealing the moon Daphnis. This tiny world is a mere 8 kilometers across, so small it would be lost in a major city on Earth. Yet its influence is immense. As Daphnis orbits Saturn, its gravity tugs on the nearby ring particles, creating ripples. Not just any ripples, but magnificent, soaring waves in the ring material on both edges of the gap. These aren't flat waves. Cassini captured images showing vertical structures like a wake, reaching up over a kilometer above and below the ring plane. It's a stunning, three-dimensional demonstration of gravity in action, a cosmic speedboat creating a permanent furrow in a sea of ice. The mechanics of this shepherding are a beautiful balance of forces. Every particle in the rings is in its own orbit around Saturn, governed by the planet's overpowering gravity. But when a particle's path brings it near a shepherd moon like Daphnis or the walnut-shaped pan in the Encode gap, it experiences an additional, tiny gravitational pull. This nudge is enough to alter the particle's velocity. If the particle is orbiting just outside the moon's gravity pulls it forward, giving it a slight energy boost that pushes it into a higher, slower orbit, effectively moving it away. Conversely, a particle just inside the moon's orbit gets tugged backward, losing a bit of energy and falling into a lower, faster orbit, which also moves it away from the moon. This coordinated push and pull from both sides acts like a celestial broom, sweeping the gap clean and preventing any stray particles from drifting back in. It's a self-reinforcing, automated maintenance system that has likely been running for millions of years. But the existence of these shepherds also presents its own layered puzzle. How do such small moons survive in this environment? One might expect them to be worn away by constant micrometeoroid bombardment or to accumulate a thick mantle of ring dust over time. Yet they persist. Their strange shapes, many look like flying saucers or ravioli, suggesting they have accreted material from the rings themselves, growing a bulky equatorial ridge. This implies a dynamic relationship. They are not just passive sculptors but active participants in a constant exchange of material with their surroundings. Their very forms are a testament to the ongoing processes within the rings. Furthermore, their precise locations and the stability of the gaps they maintain require a specific set of orbital resonances with larger, more distant moons. This means the entire ring system is a complex, interconnected clockwork, where the gentle tick of a tiny shepherd like Daphnis is synchronized with the mighty talk of a giant like Mimas, orchestrating the brilliant, structured chaos we see from afar. And just when we think we understand the clockwork precision of Saturn's rings, the system reveals a feature so strange, so seemingly supernatural, that it defies the very logic of orbital mechanics. Welcome to the mystery of the spokes. These are not solid structures, not gaps or waves, but rather ghostly, radial shadows that stretch across the rings like the spokes of a giant, ethereal wheel. They can be tens of thousands of kilometers long, yet they appear, drift, and vanish over just a few hours, behaving in a way that seems to ignore the fundamental laws that govern everything else in this realm. Here is the core of the puzzle. The rings operate under Keplerian motion. This means that the particles in the inner part of a ring orbit Saturn much faster than the particles in the outer part. It's a simple, unbreakable rule of gravity. If you were to take a photograph of a solid radial structure and then wait, the differential rotation of the rings would quickly shear it apart, twisting it into a useless spiral. Yet the spokes maintain their radial, straight-line appearance as they rotate. It's as if you drew a line with a marker from the center of a spinning record player all the way to the edge. The line would instantly become a curve. But Saturn's spokes do not curve. They persist, which implies they are not made of the same locked-in orbital ice particles as the rest of the rings. They are something else entirely, a fleeting atmospheric phenomenon painted onto the rings themselves. So, what are they? The leading theory points to a delicate and invisible force, electrostatics. The idea is that within the rings, especially in a region known as the B ring where spokes are most common, tiny, microscopic dust particles can become electrically charged. This could happen when the rings are hit by bursts of energy from the Sun, or when they are bombarded by high-energy particles from Saturn's own magnetosphere. Once charged, these tiny dust particles no longer behave like the larger, soccer ball-sized chunks of ice. Instead of being bound solely by gravity, they feel the powerful influence of Saturn's magnetic field. If they gain a negative charge, they can be electrostatically levitated, lofted right up out of the ring plane, forming a diffuse, elevated cloud of fine dust that hangs above the brighter, icy ring particles below. It is this cloud of suspended dust that creates the dark, shadowy appearance of a spoke when we view it from above. But this elegant explanation is far from complete. The exact trigger for this electrostatic levitation is still hotly debated. One compelling hypothesis involves massive, short-lived storms on the Sun. When a solar flare or a coronal mass ejection sends a flood of charged particles toward Saturn, it could suddenly and dramatically alter the plasma environment around the rings, providing the energy spike needed to launch the dust. This would explain why the spokes are more frequent during periods of higher solar activity. However, the Voyager spacecraft saw spokes during a solar minimum, suggesting there might be multiple ways to create them. Another layer of complexity is their rotation. The spokes don't rotate at the speed of the ring particles beneath them, nor at the speed of Saturn's magnetic field, which rotates like a solid object. Instead, they seem to move at a speed somewhere in between, a bizarre compromise that hints at a complex and poorly understood interplay between gravitational orbits, magnetic forces, and plasma physics. Observing the spokes is a race against time. They are transient, often forming and disappearing within a single Saturnian day. The Cassini mission, with its long orbital tour, was able to watch them evolve, confirming that they are indeed a seasonal phenomenon, coming and going with Saturn's long orbit around the Sun. But we have yet to catch one in the very act of birth, to see the precise sequence of events that conjures these cosmic phantoms into existence. Future missions may need to carry specialized dust detectors and plasma wave instruments, acting as cosmic weather stations to measure the electrical storms that ripple through the rings. The spokes are a stunning reminder that Saturn's ring system is not just a physical structure, but an electromagnetic environment, a place where invisible forces can, for a few fleeting hours, write their signatures in shadow and light for us to see. If the spokes are the ghosts of the rings, then the F-ring is their untamable rebel. While most of Saturn's rings present an image of serene, orderly structure, the F-ring is a tempest in a celestial teapot, a narrow, frenetic band of ice that is constantly kinked, braided, and contorted into impossible shapes. It's a ring that seems to have a life of its own, a dynamic ballet of creation and destruction playing out in real time. And its chaotic existence is a direct result of a relentless gravitational tug of war between two tiny, competing shepherd moons. The architects of this beautiful chaos are Prometheus and Pandora. These two small moons orbit on either side of the slender F-ring, and their relationship with it is anything but stable. Unlike the precise, maintenance-oriented shepherding we saw with Daphne's, the interaction here is far more violent and improvisational. Prometheus, the inner shepherd, has an orbit that is slightly elliptical and, crucially, slightly tilted relative to the F-ring. This means that on each of its 14.8-hour orbits around Saturn, Prometheus makes a close, plunging approach to the ring. As it dives in, its gravity doesn't just gently nudge particles. It acts like a cosmic plow, carving deep channels and pulling luminous streamers of material out of the ring's core. You can actually see these scars in high-resolution images, bright tendrils of ice reaching out into the void, dragged away by the moon's passing grasp. But the story doesn't end there. Pandora, the outer shepherd, orbits just outside the F-ring and exerts its own competing pull. The result is a gravitational ping-pong match. As Prometheus pulls material inward, Pandora's influence, combined with the natural orbital motion of the ring particles, tries to pull it back. This constant back and forth doesn't allow the ring to settle into a calm, flat disk. Instead, it gets twisted. The perturbations create brilliant kinks and clumps, and sometimes, when the timing is just right, the gravitational forces can even cause the ring to appear braided, as if multiple strands of icy pearls have been woven together by an invisible hand. What we are witnessing is orbital resonance in its most raw and dramatic form, a visible demonstration of how gravity can sculpt not just order, but also magnificent structured chaos. This leads to the central, baffling mystery of the F-ring. How does it survive this abuse? A narrow band of material, subjected to such violent and repeated gravitational assaults from two different directions, should have been shredded to nothing eons ago, its particles scattered into the void or accreted onto the moons themselves. Yet the F-ring persists, thriving in its turmoil. This resilience suggests there are hidden forces and processes at work that actively regenerate and stabilize the ring against these destructive influences. One compelling theory points to the presence of unseen, embedded moonlets within the ring itself. We have tantalizing evidence for this. The Cassini spacecraft spotted what appear to be miniature jets and fans erupting from the F-ring, features that look suspiciously like the gravitational wakes of very small, solid objects moving through the ring material. Think of these as micro-shepherds, tiny snowballs just a few hundred meters across, orbiting within the ring's core. Their localized gravity could be constantly stirring the pot, replenishing the material that Prometheus steals by nudging fresh particles into the gaps or by causing collisions that release new plumes of icy debris. In this view, the F-ring isn't a passive victim. It's a self-healing wound with internal dynamics that constantly patch the damage inflicted from the outside. Another fascinating possibility involves the very nature of the particles within the ring. They may not be solid, monolithic chunks of ice, but rather fragile, porous aggregates, fluffy snowballs that stick together loosely. When Prometheus plows through, it might not simply scatter these particles forever. Instead, the gravitational encounter could provide the energy for a grand reshuffling. Particles are pulled apart, but their low relative velocities and sticky surfaces allow them to reaccrete easily once the moon has passed, reforming the ring's structure in a different configuration. The chaos we see, therefore, might not be pure destruction, but a continuous cycle of recycling, a constant breaking apart and coming back together that gives the F-ring its frenetic, ever-changing appearance without leading to its ultimate demise. The F-ring, in all its glorious unpredictability, stands as a stunning counterpoint to the serene order of Saturn's main rings, a vibrant laboratory demonstrating that even in the clockwork of the cosmos, a little controlled chaos can be the very thing that sustains life. Imagine a spiral galaxy, its arms gracefully winding out from a brilliant core. Now shrink that cosmic whirlpool down and etch it into the shimmering ice of Saturn's rings. What you get are density waves, some of the most exquisite and finely detailed patterns in the entire solar system. These are not solid structures, but rather traffic jams in space, rhythmic compressions and rarefactions that flow through the ring particles like a wave through a crowd. They are the elegant, visible signature of an invisible force, gravitational resonance. This phenomenon acts like a cosmic metronome, setting a rhythm that the ring particles are compelled to follow, and in doing so, it writes the orbital history of Saturn's moons directly into the fabric of the rings for us to read. The entire process is a celestial clockwork of breathtaking precision. It begins with a moon like Mimas, the so-called Death Star moon due to its giant crater. Mimas orbits Saturn with a specific, unchanging rhythm. Now consider a ring particle orbiting closer to the planet and therefore moving at a faster pace. Every time this particle completes a certain number of orbits, it finds itself in the exact same position relative to Mimas. For instance, a particle in the outer part of the Cassini division, the most prominent gap in the rings, completes 2 orbits for every single orbit of Mimas. This is a 2-to-1 orbital resonance. Each time the particle swings around to that crucial point, Mimas gives it a consistent, repeating gravitational tug. It's like pushing a child on a swing. If you push at exactly the right moment in each cycle, the energy adds up and the swing goes higher and higher. In the rings, these repeated rhythmic tugs don't make particles jump higher, but they nudge them into slightly different, more eccentric orbits. This is where the magic happens. As these particles are pushed into new paths, they begin to crowd together at specific locations. Picture a multi-lane highway where one lane suddenly slows down. Cars begin to bunch up, creating a dense, slow-moving cluster. That's the crest of the density wave. Then, as the particles move on, they spread out again, creating the trough. But because this is all happening in a rotating disk, the bunching doesn't just create a single clump, it creates a spiral pattern. The wave doesn't rotate as a solid object. Instead, it propagates outward through the ring at a speed different from the orbital velocity of the particles themselves. The result is a stunning, tightly wound spiral arm made of nothing but densely packed ice particles, a fossilized record of a moon's gravitational influence. The Cassini division itself is the most dramatic example of this process. A vast region cleared clean because the resonance with Mimas was so strong it gave particles enough energy to be ejected from that zone entirely. But these waves are far more than just pretty pictures. They are a powerful diagnostic tool, a natural laboratory that allows us to weigh the rings and understand their internal properties. By meticulously measuring the exact spacing and tightness of the spiral arms in a density wave, scientists can perform a remarkable feat of cosmic deduction. The wavelength of the wave is exquisitely sensitive to the surface density of the ring, that is, how much mass is packed into a given area. It's like studying the vibrations of a drumhead to determine what it's made of. The way it vibrates tells you about the material's properties. Through this technique, the Cassini mission was able to create a detailed mass map of the rings, confirming that they are indeed extraordinarily lightweight for their staggering size. This leads to a fascinating and unresolved puzzle. The very existence of sharp, well-defined density waves tells us something crucial about the nature of the ring particles themselves. They are incredibly smooth in their interactions. For the wave to propagate cleanly over long distances, the collisions between particles must be very inelastic, meaning they stick together or slide past each other without bouncing apart violently. This suggests a low internal viscosity, a kind of gentle fluidity within the ring. If the rings were dominated by high-velocity, bouncy collisions, these delicate spiral patterns would be smeared out and destroyed almost as quickly as they form. The fact that we can see them so clearly implies a serene, orderly crowd of particles, not a chaotic mosh pit. Yet, this creates a tension with other observations. Some regions of the rings appear quite clumpy and turbulent. How can these two contradictory states, the serene flow needed for waves and the chaotic clumping we observe elsewhere, coexist? The answer may lie in the varying sizes of particles or in the different frequencies of collisions, but it remains an active area of investigation. The density waves, in all their beautiful precision, have given us a way to measure the rings, but in doing so, they have also revealed a deeper layer of complexity in their fundamental nature. Yet for all the intricate patterns and ghostly apparitions, one of the most profound revelations about Saturn's rings came not from a photograph, but from a precise and delicate measurement of an invisible force. The true mass of the ring system has long been the holy grail for planetary scientists, a single number that holds the key to untangling the deep mysteries of their age and their very creation. Think of it this way: if you were an archaeologist trying to understand the history of a great forest, you wouldn't just look at the trees. You would want to know the total biomass, the amount of life the forest sustains. In the same way, the total mass of Saturn's rings tells us about the scale of the event that formed them and provides a clock for how long they could have endured. For decades, our estimates were just that, estimates based on the rings' brightness and models of how they should behave. We knew they were vast, but were they a massive, durable structure or a surprisingly flimsy veneer? The answer was waiting to be discovered in the final, daring act of a robotic explorer. The Cassini spacecraft's grand finale was a mission-ending maneuver of breathtaking audacity. After 13 years orbiting Saturn, the spacecraft was directed into a series of 22 close passes that took it diving between the planet and its innermost rings, a region no human-made object had ever ventured before. This was not just a spectacular swan song, it was a unique scientific opportunity. As Cassini shot through this narrow gap at over 70,000 miles per hour, Saturn and its rings tugged on the spacecraft with their gravity, ever so slightly altering its velocity. By tracking the spacecraft's radio signal with exquisite precision, scientists on Earth could detect these tiny velocity changes, shifts as small as a few millimeters per second. It was a cosmic-scale version of weighing something by gently shaking it and feeling its heft. By carefully analyzing the gravitational pull of the rings alone, separated from the immense pull of the planet, the team could finally, directly weigh the entire system. The result was a staggering surprise. The magnificent, sprawling ring system, stretching over 280,000 kilometers from end to end, was found to be remarkably lightweight. The total mass is now estimated to be roughly equivalent to that of Saturn's mid-sized, icy moon Mimas. Now, Mimas is a world about 400 kilometers across, which sounds substantial until you realize that if you were to take all the material in the rings and compact it into a single body, that's all you would get. This finding was a crucial piece of evidence that powerfully supports the young rings hypothesis. A more massive ring system would have a greater reservoir of clean ice to dilute the constant rain of dark, meteoritic pollution, allowing it to stay bright for billions of years. A lightweight ring, however, is far more vulnerable. It would darken much more quickly under the same cosmic bombardment. The fact that the rings are both exceptionally bright and exceptionally lightweight creates a powerful argument that they simply have not been around long enough to become contaminated. This new measurement of mass doesn't just support the idea of youthful rings, it actively constrains the possible stories of their origin. A lower mass makes certain formation scenarios more plausible than others. For instance, the catastrophic destruction of a large, primordial moon now seems less likely, as that event would probably have scattered far more debris. Instead, the lower mass is more consistent with the breakup of a smaller, Mimas-sized body, or perhaps the disruption of a volatile, rich comet from the outer solar system. Yet, this very consistency deepens the origin mystery because, as we've seen, each of those scenarios has its own significant problems. The mass measurement is like finally finding a crucial clue in a long unsolved case, only to discover that while it eliminates some suspects, it makes the remaining ones even more puzzling. The rings are not ancient and they are not massive. They are a recent and surprisingly delicate feature, a brilliant but ephemeral crown whose true birth story remains tantalizingly out of reach, waiting for the next chapter of exploration to be written. Hidden within the seemingly smooth expanse of Saturn's B ring, the largest and most massive of the ring groups, are some of the system's tiniest and most intriguing residents. From a great distance, the B ring appears as a solid, uniform sheet of brilliant ice, but zoom in with the powerful cameras of the Cassini spacecraft and a different story emerges. Scattered across this bright canvas are thousands of peculiar, double-pronged features that look like tiny, ghostly airplane propellers. These are not solid objects we can see, but rather the gravitational signatures of unseen, embedded moonlets, each one roughly the size of a football stadium. These hidden worlds, with names like Blériot and Earhart, are not merely orbiting within the rings, they are actively trying to build themselves from the very material they are embedded in, giving us a front-row seat to the ancient and fundamental process of how planets are born. A propeller is essentially a miniature, incomplete version of the gaps created by larger shepherd moons like Daphne's. The mechanism is the same, but the scale is far smaller and the outcome is different. An embedded moonlet, perhaps only a few hundred meters across, has enough gravity to affect the ring particles immediately around it. As it orbits Saturn, it tries to clear a path for itself, pushing particles away on either side. However, the moonlet is so small and the surrounding ring material is so dense and massive that it cannot succeed in carving out a full, clean gap. Instead, it creates two partial, empty regions that trail behind and lead ahead of the moonlet, forming the distinctive S-shaped silhouette of a propeller. The ring particles are like a dense, viscous fluid flowing around a small obstacle. They are pushed aside momentarily but then flow back together, preventing a permanent opening from forming. These features are tiny. Many are just a few kilometers long, and they are transient, visible only when the lighting and viewing angles are just right, making them incredibly difficult to spot and track. What makes these propellers so profoundly important is that they represent a population of nascent moons caught in the very act of formation. The moonlets at their cores are believed to be the seeds of larger moons. In the early solar system, this is exactly how we think the planets themselves formed within the protoplanetary disk of gas and dust surrounding the young sun. Dust grains stuck together to form pebbles, pebbles aggregated into rocks, and rocks collided and coalesced into planetesimals, the building blocks of worlds. Here in Saturn's rings, we are witnessing this same process frozen in time. These moonlets are effectively planetesimals, trying to grow by accreting the icy particles around them. But they are trapped in a cosmic race against time and tide. Their location within the dense B ring puts them in a precarious position. On one hand, they have an abundant supply of building material. On the other hand, the very same orbital dynamics that govern the rings work against them. The primary force hindering their growth is something we've encountered before, the Roche limit. These moonlets are orbiting so close to Saturn that the planet's powerful tidal forces are constantly trying to tear them apart. For a loose aggregate of ice and rock, it is incredibly difficult to gravitationally collapse into a single, solid body when the surrounding planet is tugging at it more strongly than its own gravity can hold it together. This creates a fragile equilibrium. The moonlets may be growing slowly through gentle collisions, but they are also at risk of being shattered by a slightly more energetic impact. They exist in a state of quasi-stability, neither able to grow into a proper moon nor being immediately destroyed. This makes them priceless scientific specimens, offering a unique window into a critical stage of planetary formation that, until now, we have only been able to model with computer simulations. Tracking these features over time revealed another surprise. Their movement is not entirely predictable. By following specific, large propellers like Blériot across multiple years of Cassini observations, scientists noticed small but significant changes in their orbits. These deviations suggest that the moonlets are not just passive passengers, they are dynamically interacting with the ring disk in complex ways. Their gravity doesn't just create a static propeller shape, it may be causing them to migrate through the rings, locked in a delicate gravitational dance with the surrounding material. This migration is a key prediction of planet formation models, where growing planetary cores are theorized to slowly drift through the protoplanetary disk. To see this potentially happening in real time within Saturn's rings is an unparalleled opportunity to test our theories about the birth of every world in our solar system. These tiny, hidden moonlets, revealed only by the ghostly propeller scars they etch into the ice, are therefore far more than a curiosity. They are a living fossil record, a laboratory of planetary birth operating right before our eyes, showing us the ongoing struggle between creation and destruction at the very heart of a cosmic disk. But just beyond the brilliant, icy realm of the main rings, in the cold, dark expanse far from Saturn's glow, lies a ring of an entirely different character. This is the Phoebe ring, a colossal, phantom-like structure so vast it dwarfs every other ring in the system, and yet so faint it remained completely hidden from us until just over a decade ago. While the main rings are a brilliant, tightly wound disk of ice orbiting close to the planet, the Phoebe ring is a diffuse, tilted, and sprawling cloud of the darkest dust, stretching from the orbit of its namesake moon, Phoebe, all the way inward to engulf other moons. Its discovery was a monumental surprise, revealing a dimension of the Saturnian system we never knew existed, and it directly solves one of the oldest and most visually striking mysteries in the entire solar system, the two-faced nature of the moon Iapetus. The scale of this ring is almost incomprehensible. Its inner edge begins around 6 million kilometers from Saturn, and its material spreads out to a distance of over 12 million kilometers. To put that in perspective, if you could place the Phoebe ring around Earth, it would stretch from our planet all the way to the moon over 30 times. Despite its staggering size, it is incredibly difficult to see. The particles within it are microscopic, dark dust grains, and they are so sparsely distributed that the ring is virtually transparent. It wasn't discovered by direct imaging in visible light, but rather by its faint heat signature. The Spitzer Space Telescope, designed to see in the infrared part of the spectrum, detected the gentle warmth of these dust particles against the cold background of space, finally revealing the ghostly giant that had been hiding in plain sight. The source of this immense ring is the dark, irregular moon Phoebe, which orbits far beyond the main system. Phoebe is a captured object, likely a former denizen of the Kuiper belt, and it is coated in incredibly dark, carbon-rich material. It is constantly bombarded by micrometeoroids in the outer Saturnian system, and these impacts blast tiny particles of its dark surface off into space. Because Phoebe orbits in a retrograde direction, meaning it moves opposite to Saturn's rotation and the orbit of the inner moons, this ejected dust is also sent on retrograde paths. This creates a ring that is not only tilted relative to Saturn's equator, but also flows against the grain of the entire inner system. This counterflow is the key to understanding its most dramatic effect. For centuries, astronomers have puzzled over Iapetus, a moon that looks like a celestial yin-yang symbol. One hemisphere is as bright and reflective as snow, while the other is as dark as charcoal. How could such an extreme dichotomy exist? The Phoebe ring provides the elegant, if violent, explanation. As the dark, retrograde dust from the Phoebe ring spirals inward due to pressure from solar radiation, it eventually crosses the orbital path of Iapetus. But Iapetus, like almost all the other major moons, orbits in a prograde direction. From the perspective of Iapetus, the incoming dark dust isn't slowly overtaking it, it's a head-on collision. The moon is plowing through this cloud of dark material at a tremendous relative velocity, like a car driving directly into a storm of soot. The dust strikes the moon's leading hemisphere and sticks, creating a vast dark stain. This is where a powerful feedback loop takes over. The dark material on the leading hemisphere absorbs sunlight and heats up. This causes any exposed water ice on that same side to sublimate, to turn directly from a solid into a gas. This water vapor then drifts across the moon and recondenses as bright, clean frost on the colder, trailing hemisphere and the poles. This process continuously darkens the leading face and brightens the rest, creating the stark, two-toned world we see today. The Phoebe ring, therefore, is not just a passive cloud of dust. It is an active painter, using physics and orbital mechanics as its brush to create one of the most iconic and bizarre landscapes in our solar system. The existence of this immense, dark ring and its profound effect on Iapetus presents a stunning mystery of large-scale material transport. It shows that the Saturnian system is not a series of isolated zones, but a deeply interconnected whole, where processes happening in the frigid outer darkness can directly shape the appearance of a world millions of kilometers closer to the planet. It forces us to consider the entire system as a single, dynamic entity, with material constantly cycling from moons to rings and back again on a scale we are only beginning to map. This brings us to a mystery that gives all the others a profound and urgent context: the startling realization that the very phenomenon we are studying is in the process of vanishing before our eyes. We've pieced together clues suggesting Saturn's rings are young, but a far more dramatic narrative is unfolding right now. They are not just young, they are ephemeral, actively draining away in a celestial cascade that could see them disappear entirely on a cosmic timescale that is, incredibly, just a blink of an eye. The very force that holds them together, Saturn's immense gravity, is also orchestrating their demise, pulling them into the planet at a rate that shocked the scientists who discovered it. The primary mechanism behind this great vanishing act is a process we've touched on before, but its scale is what truly stuns: ring rain. The Cassini spacecraft's final orbits provided the most detailed data yet, and it revealed that this isn't a gentle drizzle, it's a downpour. Charged by sunlight and interactions with Saturn's magnetic field, tiny icy particles from the inner part of the rings are being pulled downward along the planet's magnetic field lines. They are falling into Saturn's upper atmosphere at a staggering rate, and the numbers are difficult to comprehend. Estimates suggest this ring rain is draining an amount of water equivalent to an Olympic-sized swimming pool from the rings every single half hour. This material, mostly water ice, is then interacting with Saturn's hydrogen-rich atmosphere, creating a complex chemistry that was entirely unknown before Cassini's grand finale. This process is accelerated by a kind of gravitational assist from the Sun. Saturn's rings are tilted relative to its orbit, and as the planet journeys around the Sun over its 29-year cycle, the rings present themselves at different angles to the solar wind and solar radiation. During Saturn's equinox, when the ring plane is edge onto the Sun, this ring rain appears to intensify dramatically. It's as if the changing angle of sunlight supercharges the particles, making it easier for the planet's magnetic field to grab them and pull them in. This seasonal peak in the downpour suggests that the rings are experiencing their most intense erosion right now, during this specific phase of Saturn's long year. Now, when you combine this measured rate of mass loss with the surprisingly low total mass of the rings that Cassini also determined, you arrive at a breathtaking and, for many, a worrisome conclusion. If the current rate of ring rain continues unabated, the entire magnificent ring system could be gone in as little as 100 million years. This is a worst-case scenario timeline, but it is firmly grounded in the hard data. To put that in perspective, 100 million years ago on Earth, the continents were arranged differently, and the age of dinosaurs was in its final act. In the 4.5 billion year history of our solar system, 100 million years is a fleeting moment. This means that not only are we lucky to live in an era where Saturn has rings, but we might also be living in the final glorious chapter of their existence. So why is it so difficult for scientists to give us a precise expiration date for this cosmic wonder? The uncertainty stems from the fact that we don't know if the current deluge represents a constant, long-term average or if we are simply observing a temporary peak. The rings could be experiencing a period of rapid, storm-induced loss that will slow down as their mass decreases and the system finds a new equilibrium. Furthermore, the ring rain is not the only process at work. We also have to consider the constant bombardment by micrometeoroids, which doesn't just darken the rings, it also knocks material out of orbit, either sending it drifting inward towards Saturn or outward into space. The exact balance between these different destructive forces, the gravitational pull of ring rain and the physical bombardment from outside, is not yet fully understood, making a precise countdown impossible. This impending disappearance transforms our understanding of Saturn from a static portrait to a dynamic movie, and we are witnessing a key scene. The implications are profound. It suggests that ring systems may not be rare in the universe, but they could be temporary, brilliant flashes in the pan. A star system might host a ringed giant for only a brief fraction of its history. This means that when we look at other gas giants in our own galaxy, like Jupiter or Neptune with their faint, wispy rings, we might be seeing the faded remnants of once grand systems, or perhaps systems that are only just beginning to form. Saturn, with its spectacular display, would then be the exception, not the rule, a planet caught in a brief, glorious, and highly volatile phase of its evolution. The race is now on to understand the complete life cycle of a planetary ring, from its violent birth to its slow, graceful fall into the clouds of its parent planet, a process we now know is happening right above our heads. Now, as we shift our focus from the grand, dynamic structures of the rings to the very nature of the particles themselves, we encounter a thermal mystery that has left physicists scratching their heads. This is the enigma of the ring's temperature, a puzzle that proves these bands of ice are not just visually complex but thermodynamically bizarre. When the Cassini spacecraft turned its infrared instruments toward the rings, it expected to see a relatively straightforward pattern. The side bathed in direct sunlight should be warm, and the side in shadow should be frigid. The reality, however, was completely counterintuitive. The sunlit face of the rings is significantly colder than anyone predicted, while the unlit side, shrouded in darkness, is noticeably warmer than it should be. It's as if you walked outside on a sunny day and found the air to be cool, then stepped into a deep cave and felt a surprising, gentle warmth. This thermal reversal suggests that the rings are not a simple sheet of ice. They are a sophisticated and poorly understood thermal regulation system. To understand why this is so strange, think about how everyday objects heat up. A black asphalt parking lot on a summer day absorbs sunlight and gets very hot, radiating that heat back out. The rings, being made of brilliant white ice, are naturally more reflective, so scientists expected them to be cooler than a dark surface. But the observed temperatures were even lower than those conservative models could account for. The leading theory to explain this focuses on the ring's extraordinary texture and structure. We are not looking at a solid, smooth sheet of ice, but rather a vast collection of individual particles, each one tumbling through space. This creates an incredibly porous and rough environment with countless tiny shadows and facets. When sunlight hits this jumbled surface, it doesn't just reflect off a flat plane. It penetrates deep into the gaps between particles, bouncing around in a million different directions in a process scientists call multiple scattering. Much of the solar energy is ultimately reflected back into space before it can be absorbed and converted into heat, acting like a natural planetary sunshade that keeps the rings remarkably cool. The warmth on the shaded side is the other half of this thermal puzzle. If the rings were a solid slab, the dark side would rapidly lose its residual heat to the vacuum of space and plunge to temperatures near absolute zero. But the measurements show it holds onto heat with a stubborn resilience. This points to a highly efficient internal heat transfer mechanism. The individual particles warmed on their sunlit sides are constantly colliding and interacting with their neighbors. These frequent contacts may allow heat to conduct from particle to particle, effectively transporting thermal energy from the bright side of the ring to the dark side. It's akin to a bucket brigade, where warmth is passed hand to hand through the crowd from the front lines in the sun all the way to the back in the shadows. This process, combined with the ring's fluffiness, which traps heat like a thermal blanket, prevents the unlit side from ever getting as cold as simple models would dictate. This thermal behavior has profound implications for the ring's composition and longevity. The way the rings manage heat affects the rate of a process known as thermal sublimation, where ice turns directly into water vapor without ever becoming liquid. If the rings were hotter, this sublimation would happen faster, contributing to their eventual dissipation. Their unexpected coolness may therefore be one of the factors helping to preserve them, slowing down this particular form of mass loss. Furthermore, the temperature data acts as a remote diagnostic tool, telling us about the physical properties of the ring particles that cameras cannot see. The efficiency of the heat transfer suggests particles with rough, complex surfaces that facilitate conduction rather than perfect, smooth spheres of ice. This thermal anomaly, a seemingly dry scientific measurement, thus opens a window into the micro-world of the rings, revealing a level of complexity in every individual grain of ice that we are only beginning to appreciate. While we often picture Saturn's rings as a serene and silent disk of ice, they exist within a far more active and invisible environment, the planet's immense and powerful magnetic field. This creates a dynamic and hidden relationship where the seemingly passive rings are locked in a constant, energetic exchange with Saturn's magnetosphere. This vast, invisible bubble, shaped by the planet's internal magnetic dynamo, is filled with a superheated soup of charged particles, electrons, and ions trapped by magnetic field lines. And the rings, acting as a colossal physical barrier, are constantly plowing through this seething sea of radiation, absorbing countless particles and fundamentally reshaping the space environment around the entire planet. The most direct evidence of this interaction is a phenomenon we can actually hear: a strange and periodic silence in the planet's natural radio emissions. Saturn, like Earth, emits powerful radio waves generated by charged particles spiraling along its magnetic field lines. These emissions create a steady cosmic radio broadcast. However, when the Voyager spacecraft flew past Saturn, its instruments detected something peculiar. Every time the rings passed between the planet and the spacecraft, this radio signal would suddenly and dramatically drop. It was as if someone had placed a giant, sound-absorbing blanket between the source and the listener. This ring shadow occurs because the dense material of the rings acts as a formidable shield, physically blocking and absorbing the high-energy electrons that generate these specific radio waves. The rings are so effective at this that they carve out a pronounced dark gap in Saturn's radiation belts, a region where the density of trapped charged particles plummets to nearly zero. This isn't a visual shadow, but an electromagnetic one, a silent testament to the ring's role as a giant particle sink, but the interaction is far from one-sided. While the rings are absorbing these particles, their own material is being profoundly altered by the encounter. The constant bombardment by radiation, particularly from high-energy electrons, has a dramatic effect on the chemistry of the ring particles themselves. This relentless irradiation can break apart the stable water-ice molecules on the surface of the particles, a process known as radiolysis. When a water molecule is shattered, it can release oxygen and hydrogen, but it can also lead to the formation of more complex and exotic chemicals. Scientists speculate that this process could be creating oxygen-rich compounds and may even be responsible for generating trace amounts of hydrogen peroxide or other oxidants on the icy surfaces. This means the rings are not just icy rubble. They are a vast natural chemistry set where the planet's magnetic field provides the energy to drive reactions that would never occur in a more placid environment. This electromagnetic relationship also helps explain one of the ring system's most persistent and subtle mysteries, the variable nature of the enigmatic spokes. The creation of these ghostly features is deeply tied to the plasma environment, that superheated, charged gas that permeates the space around Saturn. The leading theory suggests that on the night side of the planet, where the rings are in shadow, the balance of electrical charges can shift dramatically. Without the ionizing power of sunlight, electrons can become attached to larger, icy ring particles, giving them a strong negative charge. When morning arrives and sunlight suddenly floods the rings, it can blast these electrons away, leaving the now positively charged particles vulnerable to electrostatic levitation. Saturn's magnetic field can then easily lift these fine, charged dust grains high above the ring plane, creating the dark, radial spokes we observe. This makes the spokes not just a gravitational or optical phenomenon, but a direct weather report of the invisible electromagnetic storms that sweep through the Saturnian system. Mapping the full extent of this interaction has become a key goal for planetary scientists. The Cassini mission provided a much more detailed map of this complex relationship, confirming that different rings have vastly different effects based on their density and composition. The dense B and A rings are incredibly effective shields, creating a deep and sharp hole in the radiation belts. In contrast, the more diffuse and dusty D and E rings are far more transparent to charged particles, allowing the radiation to penetrate more deeply. Understanding this intricate interplay is not just an academic exercise, it has profound implications for the habitability of Saturn's moons. The radiation belts that are so effectively blocked by the main rings would otherwise bathe a moon like Enceladus in a deadly hail of high-energy particles, potentially sterilizing its surface and subsurface ocean. The rings, therefore, may be acting as a protective barrier, indirectly shaping the potential for life elsewhere in the system. This hidden electromagnetic dance, silent and invisible to our eyes, reveals a Saturnian system that is far more interconnected and dynamic than a simple photograph could ever suggest. This steady celestial shower, known as ring rain, is far more than a gentle drizzle. It is a dramatic and ongoing transfer of material from the rings directly into the planet, a process the Cassini spacecraft quantified with stunning precision. Imagine countless microscopic ice crystals, many smaller than a grain of sand, becoming electrically charged by the sun's ultraviolet light and by collisions. Once charged, these particles are no longer bound solely by gravity. They become susceptible to the invisible architecture of Saturn's magnetic field. They effectively hitch a ride on these field lines, which act like invisible highways that curve down from the rings and into the planet's upper atmosphere at specific latitudes. This guided fall ensures the ring material doesn't just scatter randomly, but targets distinct bands in Saturn's sky, creating a focused, planet-wide precipitation event that is actively changing the chemical composition of the air below. The consequences of this downpour were dramatically highlighted by Cassini's final, daring orbits. As the spacecraft dove between the planet and its rings, its instruments sampled this influx directly, revealing that the rain is composed not just of water ice, but also of silicates and a surprising array of organic compounds. When this mix of material plunges into Saturn's hydrogen-rich upper atmosphere, it triggers a complex and previously unknown chemistry. The water ice, for instance, interacts with atmospheric constituents to create compounds like hydrogen and oxygen, while the more complex organics likely break down into various hydrocarbons. This entire process acts as an external source of pollution for Saturn's atmosphere, introducing elements that would otherwise be in short supply and altering the balance of its high-altitude weather patterns in ways we are still working to understand. Perhaps the most startling revelation, however, was the sheer volume of this cascade. The data suggests that the ring rain is draining the equivalent of an Olympic-sized swimming pool of water from the rings onto the planet every half hour. When you extrapolate that flow rate over the entire age of the solar system, the math becomes impossible. the rings would have been completely depleted billions of years ago. This provides one of the most direct and compelling lines of evidence for their youth. The rings cannot be ancient if they are disappearing at this rate right before our eyes. Their brilliant existence today implies they either formed much more recently, or they were substantially more massive in the past, and we are witnessing the final, rapid stages of their dissolution. This ongoing mass loss inextricably links the fate of the rings to their lifespan, painting them not as a permanent fixture, but as a transient, evolving structure in its final, glorious act. Nestled at the very heart of Saturn's ring system lies its mightiest and most enigmatic component, the B-ring. This is the densest, broadest, and by far the most opaque region of the entire structure, a colossal band of ice so densely packed that it acts as a perfect celestial curtain, completely blocking any view of what lies behind it. If you were to fly a spacecraft toward it, the background stars would not just dim as they passed behind. They would be utterly extinguished, vanishing from sight as if a switch had been flipped. This extreme opacity is our first clue that the B-ring is fundamentally different from its neighbors, a place where the rules of physics seem to operate on a more intense and mysterious scale. But the true puzzle is not just how much material is there, but how that material is arranged. Deep within this brilliant, featureless wall of white, the Cassini mission uncovered bizarre and unexplained structures, sudden plateaus of unbelievable density, and deep valleys of relative emptiness that have stubbornly resisted all our attempts at a simple gravitational explanation, pointing instead to hidden processes operating between the ring particles themselves. The sheer density of the B-ring creates a paradox for scientists trying to understand its fundamental nature. We know it's massive, but its extreme opacity makes it notoriously difficult to measure just how that mass is distributed. Unlike the ring, where we can see density waves propagating cleanly, allowing us to calculate its weight, the B-ring is so choked with material that these gentle waves get lost in the noise. It's like trying to hear a single whisper in a roaring stadium. This is why the B-ring was the primary target for Cassini's groundbreaking radio occultation experiments. By transmitting a radio signal from Earth through the rings to the spacecraft, scientists could measure how much the signal was weakened. In the B-ring, the signal often dropped out completely. These experiments revealed a stunningly complex landscape hidden from our cameras, a terrain of sharp, unexplained cliffs where the density would soar to incredible peaks and sudden chasms where it would plummet. These are not the smooth, predictable patterns created by distant moons. These are jagged, chaotic features that seem to emerge from the ring's own internal dynamics. So, what could possibly cause such dramatic and localized clumping within the ring? The standard model of ring physics, which relies heavily on gravitational nudges from shepherd moons and orbital resonances, falls short here. While the gravity of a moon like Mima's does influence the outer edge of the B-ring, it cannot account for the sharp, kilometer-scale plateaus and valleys found deep within its interior. This has forced scientists to consider that the explanation lies not in the grand pull of external forces, but in the tiny, intimate interactions happening between the ring particles themselves. When two particles in the ring collide, they can either bounce off each other or gently stick together. In most of the rings, these collisions are thought to be relatively elastic, like billiard balls glancing off one another. But in the ultra-dense environment of the B-ring, a different kind of physics may take over. The particles are so crowded that their collisions may become highly inelastic. They don't bounce, they stick, forming temporary, fragile clumps. The gravity of these clumps could then attract more particles, creating a self-reinforcing feedback loop that leads to the formation of these massive, temporary plateaus of density. This idea of self-gravity wakes pushes our understanding of the rings into a new realm. It suggests that under the right conditions, extreme density and very low velocity collisions, the ring particles can effectively start to behave like a miniature galaxy, where local gravitational instabilities cause the material to spontaneously collapse into clumps and filaments. In this view, the B-ring isn't a smooth disk. It's a constantly shifting tapestry of transient gravitational aggregates, always forming and being torn apart by the differential rotation of the ring. This would naturally create the kind of jagged, unpredictable structure that the radio occultation data revealed. However, even this compelling theory runs into problems. The relative speeds of the particles, while slow, might still be just fast enough to prevent these clumps from becoming stable over long periods. The fact that we see these sharp plateaus at all implies there is another, still unknown force at work, perhaps related to the physical texture or electrostatic properties of the particles, that helps them stick together more effectively than our current models allow. The B-ring, therefore, stands as a monumental challenge, a place where the simple, elegant rules of orbital mechanics break down, and we are forced to confront the messy, complex world of granular physics on a scale we have never seen before. If the dense B-ring is a chaotic, cluttered metropolis of ice, then the neighboring ring presents a far more delicate and orderly suburb, a place where subtle, elegant patterns can persist for decades. And within this region of relative calm, we find a mystery that acts like a fossilized echo of a single, violent moment in time. Etched across vast stretches of the ring are incredibly fine, spiral ripples, resembling the microscopic grooves on a vinyl record. These are not the density waves created by the persistent gravity of moons. These are something entirely different. They are the lingering scars from a specific cataclysmic event, a trauma that shook the entire ring plane and left behind a whisper of its passing in the form of this beautiful, corrugated pattern. The existence of these ripples tells us that the rings have a memory, and that a sudden impact can write its history directly into the orbital fabric of billions of frozen particles. The leading hypothesis for the origin of these patterns is as dramatic as it is precise. Sometime in the last few decades, perhaps in the 1980s, a sizable comet or asteroid fragment, likely dozens of meters across, ventured too close to Saturn. Instead of striking the planet itself or one of the larger moons, it plunged directly through the plane of the ring. The effect would have been instantaneous and violent. As the object blasted through the ring, it didn't just push particles aside. It delivered a powerful, vertical jolt to the entire disk. Think of it like dropping a heavy stone into a perfectly still pond. The impact doesn't just make a splash, it sends a circular wave radiating outward from the point of disturbance. In the case of Saturn's rings, which are essentially a vast, flat disk, the jolt wasn't horizontal but vertical, kicking a huge swath of ring particles out of the flat plane and giving them a slight, coordinated vertical motion. This is where the real magic begins. In the weightless environment of orbit, a particle that has been nudged upward doesn't just fall back down like a ball on Earth. It enters into a gentle, oscillating motion above and below the ring plane, much like a weight bobbing on a spring. This is called vertical resonance. Initially, all the particles disturbed by the impact are oscillating in sync, creating a neat, corrugated wave at the point of impact. But the rings are governed by Kepler's laws, meaning particles at different distances from Saturn orbit at different speeds. The inner particles orbit faster than the outer ones. Over time, this differential rotation begins to shear the initial coherent wave. The inner part of the wave pattern races ahead, while the outer part lags behind, and what began as a circular ripple gradually gets wound up into a tight, spiral pattern, exactly like the groove on a spinning vinyl record. The fact that we can still see these spirals today means the event was recent enough that the pattern hasn't yet been completely smeared out by collisions and other disturbances, giving us a remarkable chance to study the aftermath of a specific cosmic collision. Yet, for all the elegance of this explanation, the precise mechanics of how the impact imparts such a clean, coordinated kick to the ring particles remains an active puzzle. An incoming object would be a chaotic, tumbling mass, and its passage through the ring would be a messy affair, likely scattering particles in all directions. How does this chaos translate into the beautifully ordered, oscillating motion we observe? Scientists believe the answer may lie in the collective behavior of the ring particles themselves. The impacting body doesn't need to hit every single particle. Instead, it creates a shock wave, a sudden, localized pressure change that propagates through the densely packed ice. This shock wave could effectively lift an entire section of the ring in a coordinated fashion, giving a vast population of particles the same initial vertical nudge. It's less like a single bullet tearing through a crowd and more like a sudden, powerful shudder that runs through the entire crowd at once, making everyone jump in unison. The ring's own self-gravity might then help to maintain the coherence of this wave as it begins its long, slow winding process. The study of these ripples provides far more than just a fascinating story of an ancient impact. It offers a powerful and novel scientific tool. By carefully measuring the exact tightness of the spiral winding, researchers can perform a remarkable feat of cosmic detective work. They can carbon date the impact event. A freshly wound spiral is loose and open. As time passes, the differential rotation winds it tighter and tighter. By measuring the current tightness of the spiral and knowing the exact orbital mechanics of the ring, scientists can effectively run the clock backward to determine the exact moment the winding began. This technique pointed to an impact in 1984, with subsequent discoveries of other spiral patterns suggesting additional impacts in other years. This turns the rings into a unique historical record, a natural archive of collisions that would otherwise have gone completely unnoticed. These delicate ripples, therefore, are not just scars, they are both a clock and a seismograph, preserving the memory of a violent day in the life of Saturn and giving us a new way to listen to the echoes of our dynamic solar system. As we pull our attention away from the chaotic F-ring and the intricate density waves, we encounter a celestial pas de deux so perfectly timed and delicately balanced it seems almost choreographed. This is the strange and beautiful dance of the co-orbital moons Janus and Epimetheus, two small, potato-shaped worlds that share nearly the same path around Saturn. They are locked in a gravitational embrace so precise that they execute a gentle, cosmic swap of positions every 4 years, a maneuver that not only prevents a catastrophic collision but also sends subtle yet powerful ripples through the fabric of the nearby rings. The mechanics of this dance are a masterclass in orbital stability. Janus and Epimetheus follow orbits that are separated by only about 50 kilometers, a trivial distance on the scale of the solar system. According to the simple laws of motion, these two moons should either collide or violently fling one another out of their shared orbit, yet they have likely been performing their swap for billions of years. The secret lies in their slight difference in mass and the elegant rules of their gravitational waltz. As the inner, slightly faster moon begins to catch up to the outer, slower one, their mutual gravity takes over. Instead of a chaotic close encounter, the inner moon transfers a tiny bit of its orbital energy to the outer one through their gravitational pull. This energy transfer acts like a gentle push. The inner moon, having lost a bit of energy, drops into a slightly higher, slower orbit. Meanwhile, the outer moon, having gained that energy, is boosted into a slightly lower, faster orbit. In effect, they seamlessly swap places. The moon that was chasing becomes the one being chased, and they begin to drift apart again, only to repeat the entire process 4 years later. It is a self-correcting, perpetual motion machine governed by gravity, a celestial seesaw that has found a perfect equilibrium. The influence of this delicate dance, however, extends far beyond the two moons themselves. Their regular 4-year swap creates a periodic gravitational pulse, a rhythmic tapping on the vast disk of Saturn's rings that lies just inside their orbit. This consistent tapping acts like a metronome, setting off a series of spiral density waves within the ring particles. These waves are not the simple, single spirals we see from larger, more distant moons. They form an incredibly complex, interwoven pattern. Because the swap happens periodically, it creates multiple overlapping wave patterns, each with a slightly different frequency and origin point. The result is an intricate tapestry of bright and dark bands within the rings, a direct and visible transcription of the moon's gravitational rhythm. Yet, for all its elegance, this system presents a formidable challenge for astrophysicists. When researchers create sophisticated computer models to simulate the Janus-Epimetheus swap and its effect on the rings, the virtual rings they generate never quite match the exquisitely detailed patterns we actually observe from spacecraft like Cassini. The models get the broad strokes right, the timing, the general location of the waves, but they fail to replicate the fine-scale structure, the sharpness of the wave crests, and the precise interactions between different waves. This discrepancy is a crucial clue that our understanding of the ring's physical properties is still incomplete. The failure of these models to perfectly replicate the waves tells us that there are hidden variables at play within the ring environment itself. The models typically assume the ring particles are smooth, uniform spheres of ice that interact in simple, predictable ways, but the reality is far messier. The particles likely have irregular, porous shapes and a wide range of sizes, from tiny dust grains to house-sized boulders. These differently sized particles respond to gravitational tugs in different ways and collide with each other with varying degrees of stickiness and bounce. This complex granular physics, which is extraordinarily difficult to model, adds a layer of noise and texture to the waves that our current simulations cannot capture. The imperfect rings in our computers are therefore a gift. They highlight the subtle forces of friction, viscosity, and particle size distribution that we are still striving to quantify. The ever-changing pattern woven by Janus and Epimetheus acts as a natural laboratory, a cosmic loom whose intricate product we can observe but not yet fully reproduce, pushing us to refine our theories of how matter behaves in these vast spinning disks. Now, as we journey closer to the planet itself, we leave behind the brilliant, dense architecture of the main rings and enter a realm of almost ethereal fragility. This is the D-ring, Saturn's innermost ring, a place so delicate and faint it was the last of the major rings to be discovered, and it remains one of the most mysterious. Unlike the bold, reflective bands of the B and A rings, the D-ring is a ghostly, wispy veil of material, more like a sheet of fine gauze stretched across the void. It is a ring in its most elemental and vulnerable state, a place where the slightest gravitational or electromagnetic nudge can sculpt its structure in ways that completely defy the orderly, predictable clockwork we see further out. And within this tenuous cloud, we find some of the ring system's most baffling features: strange, isolated strands of material that coil and uncoil like cosmic springs, behaving as if they are dancing to a tune we cannot hear. The D-ring's delicate nature is a direct consequence of its location. It resides perilously close to Saturn, beginning only about 66,000 kilometers from the planet's cloud tops. At this intimate distance, the planet's gravitational influence is overwhelming, and the ring is subjected to powerful tidal forces that constantly work to pull it apart. Furthermore, it is embedded deep within Saturn's immense magnetosphere, bathed in a dense soup of charged particles and subject to the planet's powerful magnetic field. It also skims the very top of Saturn's extended upper atmosphere, creating a constant, slight drag that slowly saps the orbital energy of its particles. This combination of extreme forces, gravity, electromagnetism, and atmospheric friction makes the D-ring an inherently unstable and transient environment. Its particles are not the durable, soccer ball-sized chunks of ice found in the B-ring, but are instead microscopic, fine dust, more akin to smoke than to snow. This dusty composition is why it appears so faint and sheet-like. It lacks the solid, reflective surfaces of larger ice blocks, scattering sunlight in a soft, diffuse glow. The most mesmerizing features within this faint ring are its mysterious ringlets. These are not the clean, empty gaps carved by shepherd moons, but rather bright, narrow strands of concentrated material that seem to float within the surrounding haze. The Cassini spacecraft observed these ringlets in stunning detail, and what it found was utterly perplexing. While the majority of the D-ring material orbits Saturn in a placid, unstructured sheet, these isolated ringlets exhibit bizarre, independent motions. Some appear to be tightly wound spirals, while others seem to be slowly rotating or precessing as a single, cohesive unit. This unified motion is the core of the mystery. In a system ruled by Kepler's laws of differential rotation, where inner particles orbit much faster than outer ones, any solid, radial structure should be instantly sheared into a useless spiral. The fact that these ringlets maintain their coherence as they slowly pivot suggests that the individual dust grains within them are not just following independent orbits. They are somehow bound together, moving in lockstep as if connected by an invisible force. This is where the standard model of ring physics, which relies almost entirely on gravity, completely fails. The gravitational pull of the tiny particles on each other is far too weak to overcome the shearing effect of their different orbital speeds. So, scientists have been forced to look for other, more exotic forces that could provide this cohesion. The prime suspect is Saturn's powerful magnetic field. The fine dust particles of the D-ring, constantly bombarded by radiation, can easily become electrically charged. Once charged, they are no longer just subject to gravity, they become susceptible to electromagnetic forces. It is possible that these particles are aligning themselves along the planet's magnetic field lines, effectively using magnetism as a kind of cosmic glue to hold their structure together against the relentless tug of gravity that tries to pull them apart. The ringlet would then rotate not at the orbital speed dictated by gravity alone, but at a speed influenced by the rotation of Saturn's magnetic field itself, which turns like a solid object. This could explain their strange, unified precession. Another compelling theory points to a much more local and invisible influence, Saturn's own upper atmosphere. The D-ring is so close to the planet that its outermost particles are essentially skimming the top of the atmosphere. This creates a constant, gentle friction. While this drag would normally cause particles to lose energy and spiral inward, it might also, under specific conditions, have a synchronizing effect. If the atmospheric drag is just right, it could act to equalize the orbital energies of particles within a narrow band, forcing them into a shared rhythm and creating a stable, rotating pattern. This would be like the way wind blowing across a body of water can organize random ripples into orderly, parallel waves. The true explanation might even be a complex combination of both effects, a delicate interplay between magnetic alignment and atmospheric drag that creates these fleeting, structured harmonies within an otherwise chaotic and disintegrating environment. The D-ring, in all its wispy fragility, is therefore more than just a ring. It is a supremely sensitive instrument, its every strand and ripple a direct measurement of the invisible forces that surge and swirl in the space immediately above the giant planet. Surrounding the faint and enigmatic G-ring, a delicate band of dust located far beyond the main rings, lies one of the most exquisite examples of celestial confinement in the Saturnian system. This is not a continuous, uniform loop of material, but rather features a brilliant, isolated arc, a concentrated ribbon of brightness that shines with surprising intensity against the dim backdrop of the ring. For years, this arc presented a fundamental puzzle. In a system governed by differential rotation, where inner particles orbit faster than outer ones, any such concentration of material should be rapidly smeared out into a full, evenly distributed ring within just a few decades. The very existence of this sharp, well-defined arc implied that some powerful, localized force was actively corralling the particles, holding them in a cosmic pen against the relentless tide of orbital mechanics. The answer to this riddle was found in the subtle, yet persistent, gravitational influence of a moon so small it was not discovered until the Cassini mission had been observing Saturn for several years, Aegeon. This tiny moon, a mere 500 meters across, is the key architect of the G-ring arc. It orbits Saturn nestled within the arc itself, and its gravity creates a region of stability known as a co-rotation resonance. Imagine Aegeon as a shepherd, but instead of clearing a gap, its gravity creates a safe zone, a gravitational well where particles can become trapped. The mechanism is one of precise timing. As dust particles within the G-ring orbit Saturn, they are continually subjected to the tiny gravitational tugs from Aegeon. Particles that have orbital periods that are a simple fraction of Aegeon's own orbit, a 7-to-6 resonance in this case, receive a repeated, rhythmic nudge at the same point in their path every 7 of their orbits. These consistent, gentle kicks act to cancel out the natural tendency of the particles to drift apart, effectively confining them to a specific longitudinal segment of the ring. It's a delicate orbital dance where the moon's gravity provides a metronome-like beat that keeps the particles marching in sync, preventing them from spreading out into a uniform disk. Yet, gravitational confinement alone is not the entire story. An arc of bright, fresh material also requires a source to replenish it, as the constant micrometeoroid bombardment and the relentless pull of solar radiation would otherwise grind the particles down and disperse them over time. This points to a dynamic cycle of creation and destruction. Scientists believe the primary source of the arc's material is Aegeon itself, along with other even smaller, unseen bodies trapped within the same resonant region. These diminutive moons are constantly being pelted by micrometeoroids, and each impact blasts tiny particles of ice and dust off their surfaces. This newly ejected debris is then immediately swept up into the gravitational corral of the resonance, adding fresh, bright material to the arc. The arc we see is therefore not a static collection of dust. It is the visible plume of an ongoing excavation, a continuous spray of ejecta from a celestial quarry that is being actively mined by the random violence of space. This creates a breathtakingly delicate balance. The arc represents an equilibrium between the source of new material from impact events and the destructive forces that work to remove it. The same solar radiation pressure that helps define the arc also acts to erode it, slowly pushing the smallest particles out of the resonance and dooming them to drift away. The stability of the arc over the years we have observed it suggests that the rate of new material being blasted off Aegeon and its sibling moonlets is in a near-perfect balance with the rate at which material is being lost. This makes the G-ring arc a transient and highly sensitive phenomenon. A slight increase in the local micrometeoroid flux could make the arc brighter and more pronounced, while a period of calm could allow it to fade. Its very presence is a testament to a perfectly tuned, ongoing celestial process, a fragile ribbon of light whose continued existence depends on a constant, gentle rain of cosmic impacts and the unwavering gravitational guidance of a moon barely larger than a skyscraper. But nestled between the stately A ring and the chaotic F ring lies a region that defies our simple labels, a place that is neither a clear emptiness nor a dense band of ice. This is the Roche division, a gap that is not truly a gap, a void that is actually full of activity, serving as a dynamic boundary where the competing forces of gravity and accretion wage a constant, quiet war. We often think of gaps in the rings as being pristine, swept clean by the gravitational might of a single shepherd moon. The Roche division, however, presents a far more complex and intriguing reality. It is a sprawling frontier populated by a faint haze of dust and a collection of enigmatic tiny moonlets, and its very existence challenges our understanding of where a ring ends and where a collection of small moons begins, illustrating the fluid and complex gravitational architecture that governs the entire Saturnian system. The name itself offers the first clue to its significance. The Roche division is named for the French astronomer Édouard Roche, who first calculated the critical distance from a planet now known as the Roche limit. This is the theoretical boundary inside which the tidal gravitational forces from the planet are stronger than the internal gravity holding a moon together. Any sizable object made of loose material that ventures inside this limit would be torn apart by Saturn's immense pull. The rings themselves exist almost entirely within Saturn's Roche limit, which is why we see countless particles instead of a single solid moon. The Roche division sits within this zone of tidal destruction, acting as a kind of gravitational no-man's land. Its relative emptiness is not the work of a single moon like Pan or Daphne's, but rather a consequence of this fundamental orbital environment. The region is dominated by a powerful gravitational resonance with the moon Mimas, the same resonance that clears the much larger Cassini division. Here, however, the effect is different. The resonance doesn't create a perfectly clean void. Instead, it prevents the material from coalescing into a denser ring, maintaining a tenuous, sparse collection of particles that are continually jostled by these persistent tidal forces. This leads to the central mystery of this division. If it's a region defined by gravitational forces that inhibit the formation of large bodies, why is it populated at all? The answer reveals that the Roche division is not an empty gap, but a bustling crossroads of cosmic traffic. The Cassini spacecraft revealed this region to be filled with a faint, ethereal ring of fine dust, material that is simply too small to be easily seen from Earth. More strikingly, it is home to a collection of small, irregular moonlets like Methone, Pallene, and Anne. These are not the powerful shepherds of the F-ring. They are small, porous bodies, often just a few kilometers across, that look more like battered rubble piles than proper moons. Their presence in a zone of tidal destruction is a paradox. They exist in a fragile equilibrium, constantly on the verge of being pulled apart, yet they persist. Scientists believe these moonlets are not dense, solid rocks, but rather extremely porous aggregates, fluffy collections of ice and dust held together by their own weak gravity. Their low density and loose structure may allow them to better withstand the tidal forces that would shatter a more solid object, acting like a flexible sponge that can absorb the strain where a rigid brick would fracture. The relationship between these moonlets and the surrounding dust is a dynamic cycle of creation and destruction. These small worlds are the likely source of the fine material that fills the division. They are constantly bombarded by micrometeoroids, and each impact scours their surfaces, blasting tiny particles of ice into orbit around Saturn. This creates a faint, co-orbital ring of dust that travels along with each moonlet, a personal cloud of debris that marks its path. We see this most clearly with the moon Anne, which shares its orbit with a faint, arc-shaped ring of material, a feature created by a specific gravitational resonance with the larger moon Mimas. This process turns the Roche division into a laboratory for studying the life cycle of ring material. It is a place where small moons are actively eroding, feeding dust into the surrounding space, and where that same dust might also be slowly re-accreting back onto the moonlets in a slow-motion cycle of erosion and renewal. The division is not a static boundary, but a vibrant ecosystem of material exchange. Ultimately, the Roche division forces us to abandon our simple definitions. It is not a clean break between the rings, but a transitional zone, a bridge between the organized chaos of the dense rings and the more solitary existence of the small moon. Its populated emptiness challenges the very categories we use to describe the Saturnian system. Is it a gap in the rings, or is it the outermost ring of a collection of moons? The answer is both and neither. It exemplifies that the architecture of Saturn's rings is not a series of separate, distinct features, but a continuous spectrum of material, from fine dust to giant moons, all governed by the delicate and perpetual balance between the planet's disruptive gravity and the fragile, persistent tendency of matter to clump together. It is a humbling reminder that nature rarely draws hard lines, preferring instead to create rich and complex frontiers where different states of matter coexist in a beautiful gravitational dance. This very question, why a vast disk of orbiting particles hasn't simply collapsed under its own gravity to form new moons, strikes at the heart of celestial mechanics and leads us to one of the most fundamental forces shaping the Saturnian system, the Roche limit. Named for the French astronomer Édouard Roche, this isn't a physical boundary you can see, but rather a theoretical line in space, a gravitational balancing point. Inside this critical distance from a planet, the tidal forces, the difference in gravity between the side of an object closest to the planet and the side farthest away, becomes stronger than the object's own self-gravity, the force that holds it together. Imagine you are a small moon made of loose rubble and you venture too close to Saturn. The planet's gravity pulls much more strongly on the side of you facing the planet than on the side facing away. This difference in pull creates a stretching force, and if you cross that Roche limit, this tidal stretching overcomes your own weak gravity. You are no longer able to hold yourself together, and you are progressively pulled apart, shredded into the countless particles that now make up the rings. This is the primary reason the rings exist as a disk rather than a single, solid body. Saturn's gravity actively prevents the material from coalescing. Yet, this elegant explanation is not the complete story. If you look closely enough, the rings are not a perfectly smooth and homogeneous sheet of independent particles. Within the densest parts of the B ring, for instance, scientists have observed strange, transient patterns that suggest a constant, low-level struggle between disruption and cohesion. These are not the organized spiral of density waves from moon resonances, but something far more chaotic and intimate. They are known as self-gravity wakes. Think of them not as solid objects, but as temporary traffic jams in a celestial highway, where the mutual gravitational attraction between nearby particles causes them to clump together briefly, only to be torn apart moments later by the relentless differential rotation of the ring. This creates a landscape that is constantly flickering, with regions of slightly higher density forming, stretching into elongated streaks, and then dissolving back into the background, all within a matter of hours. It's a dynamic equilibrium, a perpetual dance where gravity tries to build and orbital motion insists on tearing down. The existence of these self-gravity wakes is a crucial piece of the puzzle, revealing that the rings are in a state of delicate balance. For these transient clumps to form at all, the ring must be dense enough that particles are close enough for their mutual gravity to be significant. However, for the clumps not to collapse permanently into moonlets, the random motions and shear forces within the ring must be strong enough to disrupt them. This balance depends on factors like the overall density of the ring, the size distribution of the particles, and how sticky or bouncy they are when they collide. This is where our computer models run into profound challenges, simulating the behavior of trillions of individual particles, each with its own gravity, colliding and interacting in a disk experiencing immense tidal forces, is a computational task of almost unimaginable complexity. The models that come closest to replicating what we see suggest that the rings are in a crossover regime, where gravity is just strong enough to cause this clumping instability, but not strong enough to win the war and form a moon. This dynamic struggle provides a stunning, real-time glimpse into the very processes that built our solar system. The protoplanetary disk that swirled around our young sun was a vastly more massive version of Saturn's rings. Within that disk, dust grains collided and stuck together, eventually forming planetesimals, the building blocks of planets. What we see in Saturn's rings with its self-gravity wakes is this same process of accretion trying to begin, but being suppressed by the overwhelming tidal power of the planet. The rings are a frozen, or more accurately, a perpetually frustrated snapshot of planetary birth. They show us the initial conditions and the physical rules, but they also show us the limiting factor, the Roche limit, that prevents the process from reaching its ultimate conclusion. This makes the rings a priceless natural laboratory, allowing us to study the fundamental physics of accretion disks in a context we can observe up close, testing our theories about how every world from Mercury to Pluto first began to form from the dust of a newborn star. For centuries, we've admired Saturn's rings as a uniform band of brilliant white, a perfect celestial halo. But the view from close range reveals a far more nuanced and colorful reality. When the Cassini spacecraft sent back its high-resolution images, it uncovered a subtle but distinct gradient of color painted across the rings, a cosmic watercolor of clues about their history and composition. The most striking difference lies between the staggering brightness of the B ring and the more muted, almost dusky appearance of the C ring and the broad, dark swath of the Cassini division. Where the B and A rings shine with the stark whiteness of fresh snow, these other regions take on a noticeably darker reddish-brown or even taupe hue. This isn't a trick of the light. It's a direct chemical fingerprint, a visible record of what has happened to these different regions over millions of years, telling a story of contamination, exposure, and the relentless reign of cosmic pollution. These color variations are a direct window into the composition of the ring particles themselves. The brilliant white of the B and A rings confirms what spectrometers have told us. They are composed of nearly pure water ice, which reflects almost all sunlight across the visible spectrum. The darker, reddish tones in the C ring and Cassini division, however, point to the presence of contaminating material mixed in with or coating the icy particles. The specific reddish-brown color is a crucial clue. On Earth, we see similar colors in rust, which is iron oxide, and in certain types of complex organic compounds often called tholins. These tholins are not a single substance, but a class of reddish, tar-like macromolecules formed when simple carbon-containing compounds like methane are exposed to ultraviolet radiation or other forms of energy. Their presence across the solar system, from the surface of Saturn's moon Iapetus to the plains of Pluto, marks them as a common byproduct of cosmic chemistry. So, the simple presence of a reddish tint tells us that the darker ring regions are contaminated, but the precise shade hints at the likely contaminants being a mix of iron-bearing minerals and complex organics. This naturally leads to the question of why this contamination isn't spread evenly. If the entire ring system is being bombarded by the same rain of micrometeoroids, why are some regions still pristine while others are visibly soiled? The answer lies in the dramatically different densities and environments of each ring. The B ring is an incredibly dense, packed metropolis of ice. Its particles are so close together that the constant, gentle collisions between them may act like a natural polishing mechanism, continually fracturing particles and exposing fresh, clean ice from their interiors. Furthermore, its immense density means that any incoming dark dust is vastly outnumbered by bright ice particles. A little bit of pollution gets diluted in a huge volume of white, having a minimal effect on the overall color. It's like adding a cup of dark soil to a giant white sand beach. You'd hardly notice the difference. The C ring and the Cassini division, in contrast, are the sparse suburbs of the ring system. They are far less dense, meaning there are fewer icy particles to dilute the contaminating material. A single micrometeoroid impact or a coating of dark dust on a particle here has a much greater visual impact because there's simply less bright ice surrounding it to overwhelm the dark signal. But there's likely more to the story than just simple dilution. The environment within these sparser regions might also be less effective at cleaning itself. With fewer collisions, there is less opportunity to fracture particles and expose fresh ice. The contaminants can build up into a more permanent, mature patina on the particle surfaces. Additionally, some scientists speculate that Saturn's own magnetic field could be playing a role in sorting this material. The finer, darker dust particles, once charged, might be more easily transported by electromagnetic forces out of the dense B ring and into the less dense C ring and divisions, effectively concentrating the pollution in these specific areas over millions of years. The color of the rings, therefore, is not just a pretty detail, it is a vivid timeline of environmental history. The brilliant white of the B ring suggests a region that is either very young or incredibly effective at self-cleaning, constantly renewing its surface. The darker, reddish tones of the C ring and Cassini division speak of older surfaces, or at least regions that have been more passive, quietly accumulating the grime of the solar system for a much longer time. This color map provides a critical independent line of evidence that supports the idea of a complex and varied life history for the different parts of the ring system. They have not all evolved in lockstep. Some regions have remained vibrant and active, while others have settled into a quieter, more stained old age, their colors serving as a lasting testament to the different challenges and conditions they have endured. Far from the brilliant, structured chaos of the main rings, in the cold, spacious realm beyond Saturn's traditional boundaries, lies a ring of an entirely different nature. This is the E-ring, a vast, ethereal halo so faint and diffuse it is almost invisible, a cosmic phantom stretching from the orbit of Mimas all the way out past the moon Dione. For years, its origin was a complete mystery. It was too wide, too tenuous, and its particles were too fine to have been formed by the same processes that shaped the inner rings. The puzzle was solved in one of the most spectacular discoveries of the Cassini mission, a revelation that connected this ghostly ring directly to one of the most geologically active worlds in the solar system. The E-ring is not a static structure, it is a living plume, a continuous, real-time exhalation from the tiny, icy moon Enceladus, whose south pole is home to a series of massive, roaring geysers that blast water ice and organic compounds directly into space. The mechanism behind this celestial connection is as dramatic as it is elegant. At the south pole of Enceladus, 4 prominent fractures known as the tiger stripes slice across the icy crust. These are not dormant cracks, they are actively venting, acting as nozzles for a series of powerful cryovolcanic jets. Cassini flew directly through these plumes and confirmed they are composed primarily of water vapor with a surprising mix of salts, silica nanoparticles, and simple organic molecules like methane and propane. The energy driving this incredible activity comes from the relentless gravitational squeezing Enceladus experiences as it orbits Saturn. The moon is caught in an orbital resonance with its larger sibling Dione, a gravitational tug of war that flexes and stretches Enceladus's interior. This tidal heating is so intense that it maintains a global, liquid water ocean beneath the moon's frozen shell, an ocean that is in direct contact with a rocky core at the seafloor. The heat from this core warms the water, which then rises and forces its way up through the tiger stripes, exploding into the vacuum of space as a towering column of ice and vapor. This is where the E-ring is born. Each tiny ice grain ejected from Enceladus becomes a new citizen of the ring, but the journey of these particles is far from simple. The initial blast from the geysers gives them a kick, but it is the pressure of sunlight that truly shapes the ring's grand architecture. Solar radiation exerts a gentle but constant push on these microscopic grains, a force known as radiation pressure. This force acts like a cosmic sculptor, slowly altering the orbits of the smallest and brightest particles and spreading them out over millions of kilometers to form the vast, donut-shaped cloud we observe. The ring is not uniform. It is brightest and densest at the orbit of Enceladus, its source, and thins out dramatically as you move away. This dynamic process means the E-ring is not a permanent structure. Its particles have a limited lifespan. They are constantly being lost to space, spiraling inward toward Saturn, or colliding with other moons. Its continued existence is entirely dependent on the ongoing eruptions from Enceladus, making it the only ring in our solar system that is actively and continuously regenerated by a known localized source. The composition of the E-ring's ice grains, however, is what transforms this from a beautiful astronomical phenomenon into a frontier for astrobiology. When Cassini's instruments tasted the plume, they didn't just find pure water ice. They found a cocktail of ingredients that point directly to a complex and potentially habitable environment. The discovery of sodium salts and tiny particles of silica was a landmark moment. These are not materials that could have been formed in the cold vacuum of space or in a simple, frozen ice sheet. Their chemical signature points unmistakably to liquid water interacting with a rocky seabed at high temperatures. The silica particles, in particular, are the right size and composition to have been formed in hydrothermal vents on the ocean floor of Enceladus, where hot, mineral-rich water is gushing out into the cold ocean. This is a direct analog to the deep-sea hydrothermal vents on Earth, which are teeming with life, ecosystems that thrive in total darkness, powered not by the sun but by chemical energy. The presence of these grains in the E-ring is like receiving a bottled message from the deep ocean of another world, telling us that the conditions for life as we know it, liquid water, a source of energy, and the necessary chemical building blocks, may exist just beneath the icy shell of this small, distant moon. This profound connection makes the E-ring more than just a ring. It is a celestial delivery system, a mechanism that samples the interior of a potentially habitable world and broadcasts its contents across the Saturnian system. The material from Enceladus doesn't just form the ring, it also falls as a gentle snow onto other moons, potentially altering their surfaces and providing a source of fresh water and organics. The existence of the E-ring, therefore, forces us to consider the entire Saturnian system as a deeply interconnected biological environment. The geysers of Enceladus and the vast, shimmering ring they create stand as one of the most compelling arguments for the potential of life beyond Earth, a stunning reminder that sometimes the grandest secrets are not hidden in plain sight, but are being actively launched into the sky, waiting for us to reach out and catch them. And if the ebb and flow of ring rain gives us a glimpse of the ring's long-term fate, there is an even more immediate and observable transformation underway, forcing us to abandon the idea of Saturn's rings as a timeless museum piece and embrace them as a living, breathing, and rapidly changing system. This is the mystery of their time-variable phenomena, the startling realization that in the mere 4 decades since the Voyager probes first gave us a close-up view, significant and inexplicable changes have already been recorded. The rings we see today are not the same rings that Voyager photographed in the early 1980s, and they will likely be different again when our next robotic emissary arrives. This mutability transforms them from a static celestial portrait into a cosmic movie, and we are fortunate to have captured a few crucial frames. One of the most dramatic shifts involves the very phantoms we discussed earlier, the enigmatic spokes. When the Voyager spacecraft first revealed these radial shadows sweeping across the B-ring, they were abundant, dark, and easily visible. For a time, they became a defining characteristic of the ring system in the minds of planetary scientists. Yet, when the Cassini mission entered orbit around Saturn in 2004, it saw something very different. The spokes had all but vanished. They were faint, rare, and difficult to spot. It wasn't until several years into Cassini's mission, as Saturn moved towards its equinox and the Sun shone directly on the ring plane, that the spokes began to reappear with their former vigor. This clear correlation with Saturn's seasons is a powerful clue, pointing directly to the Sun's role in their creation. It seems that the angle of sunlight is critical for charging the tiny dust particles, perhaps by altering the plasma environment around the rings or by changing the rate at which electrons are knocked off the icy grains. The spokes, therefore, are not a constant feature but a seasonal one, a form of ring weather that comes and goes with Saturn's long 29-year journey around the Sun. But the changes are not limited to these ghostly apparitions. Broader, more subtle variations in the overall brightness and reflectivity of the rings have also been tracked over time. Different regions of the rings appear to brighten or dim in ways that are not yet fully understood. Some of this is undoubtedly linked to the same seasonal shifts that control the spokes. As the Sun's angle changes, it illuminates the countless vertical structures within the rings, the wakes of tiny moonlets and the ragged edges of density waves, in different ways, casting long shadows or flooding them with light. However, some variations might be driven by more fundamental processes, such as temporary surges in the rate of micrometeoroid bombardment that darken a specific region, or by internal collisions that expose fresh, bright ice. The rings are a system in a delicate equilibrium, and even small nudges can shift their appearance on human timescales, not just geological ones. This observed dynamism presents a profound challenge to scientists trying to build comprehensive models of the ring system. A model that perfectly explains the rings as Cassini saw them in 2008 might fail to account for their appearance in 1981 or in 2040. It forces researchers to incorporate time as a critical variable. The rings are not in a steady state. They are a fluid and reactive environment whose properties, their particle size distribution, their dust content, their plasma charge are in constant flux. The fading and return of the spokes, for instance, is a natural experiment providing a test bed for the various electrostatic theories. If a model can accurately predict when and where the spokes will appear based on the Saturnian season and solar activity, it will have passed a crucial test. The ring's changing face is therefore not just a curiosity. It is the key data that will help us discriminate between competing hypotheses about their inner workings. Ultimately, the time-variable nature of the rings closes the loop on our exploration, connecting their grand billion-year life cycle to the intimate changes we can witness in a single human lifetime. It underscores that we are not studying a fossil, but a living, evolving entity. The same forces that will one day drain the rings away entirely, the gravitational tugs, the solar radiation, the micrometeoroid rain, are the very forces that paint the spokes, shift the brightness, and sculpt the patterns we see today. To watch the rings change is to watch planetary evolution in fast forward, a privilege that reminds us the cosmos is not a still life, but a vibrant and ever-unfolding story, and around Saturn, we are reading one of its most captivating chapters in real time. And so we arrive at the final, overarching enigma, a question that gives profound meaning to every clue and puzzle we have explored. What is the ultimate destiny of Saturn's rings? Are we watching a fleeting cosmic performance, a single, brilliant act in the long play of the solar system? Or is this display part of a grander, cyclical rhythm of death and rebirth? The evidence we have gathered paints a compelling, albeit complex, portrait of a system in flux, forcing us to confront the impermanence of even the most majestic celestial structures. The case for a fleeting existence is powerful and sobering. The brilliant reflectivity of the rings, their surprisingly low mass, and the dramatic, ongoing downpour of ring rain all point toward a system that is not only young but actively disintegrating. Imagine a magnificent ice sculpture carved under a temporary sun. It is stunning, but it is already melting. The rings are that sculpture, and the measurements from Cassini's grand finale suggest the meltwater is flowing at a torrential rate. If this cascade continues unabated, the entire vast structure could be drained into Saturn's atmosphere within a mere 100 million years. This isn't a distant, abstract future. It's a timescale in which the continents on Earth were still recognizably taking their modern forms. This perspective frames our current view of Saturn as a moment of extraordinary privilege. For the vast majority of its 4.5 billion-year history, the planet was likely a ringless giant, and in a future not too far away, it may return to that solitary state. We just happen to be alive during the brief cosmic window when its jewelry is on full, glorious display. However, nature rarely operates in simple, linear narratives. An alternative, more cyclical view proposes that the rings are not in their death throes, but could be in a state of dynamic equilibrium, or even in a prolonged middle age. This theory questions whether the current intense ring reign is a permanent feature or a temporary surge, perhaps linked to Saturn's seasonal cycles or to a recent increase in solar activity. Could the rings be far more massive and resilient below their visible surface, with a deep reservoir of older, darker material that we cannot easily see, providing a buffer that extends their lifespan? Furthermore, the presence of embedded moonlets and the constant recycling of material through collisions suggest a system with a robust, if fragile, ability to heal itself. Perhaps the rings are not simply vanishing, but are instead undergoing a slow metamorphosis, steadily evolving from a bright, icy system into a darker, dustier one that could persist for much longer, albeit in a far less spectacular form. This leads to a truly captivating speculation, the possibility of a cycle of destruction and reformation. We have strong evidence that a catastrophic event, like the shattering of a comet or a moon, created the rings we see today. If such an event can happen once, what is to stop it from happening again? The Saturnian system is a gravitational shooting gallery, filled with moons and frequented by icy wanderers from the outer solar system. It is entirely plausible that the eventual disappearance of the current rings would not be the final word. In 100 million years or a billion, another celestial intruder could venture too close, cross the Roche limit, and be torn asunder, seeding the void with a new generation of icy debris. In this grander view, Saturn may be a planet that periodically adorns itself, its rings flashing into existence and fading away over and over again across the eons, a pulsing heartbeat in the life of a gas giant. The ultimate fate of the rings, therefore, is more than an astronomical curiosity. It forces a profound shift in how we perceive our place in the cosmos. If Saturn's rings are truly ephemeral, then their breathtaking beauty is imbued with a precious, poignant rarity. It means that the iconic image we hold of our solar system is not a permanent fixture, but a temporary alignment of matter and time. Their potential disappearance would fundamentally alter the Saturnian system. The powerful electromagnetic shadow they cast would vanish, allowing harsh radiation to bathe inner moons like Enceladus, potentially impacting any potential habitats in its subsurface ocean. The delicate gravitational dances with shepherd moons would cease, and the celestial artistry of density waves would be silenced. The system would become quieter, darker, and profoundly different. Whether we are witnessing a birth, a graceful aging, or a final, glorious act remains the greatest mystery of all, a humbling reminder that the universe is a theater of constant change, and we are the fortunate audience for one of its most stunning shows. So here we are at the end of our journey, having traveled through 25 mysteries that transform Saturn from a distant picture of serenity into a cosmic engine of bewildering activity. We began by questioning their very age, confronting the startling evidence that these brilliant rings may be a youthful addition to the solar system, a spectacle that appeared long after the dinosaurs and may vanish again in a cosmic blink. We grappled with their impossible purity, a gleaming whiteness preserved by either a recent, violent birth or hidden self-cleaning processes we are only beginning to understand. We saw the celestial architects, the shepherd moons, carving pristine gaps and sculpting edges with gravitational precision, while their chaotic cousins, Prometheus and Pandora, twisted the F-ring into a frenetic ballet of kinks and braids. We witnessed ghostly spokes materialize and fade like cosmic phantoms, driven by invisible electrostatic storms, and we read the history of moon orbits etched into the rings as exquisite spiral density waves. We learned that the rings have weight, a surprisingly light mass that hints at their ephemeral nature, and we discovered tiny propellers, the signatures of hidden moonlets caught in the very act of trying to form new worlds. We explored the vast, dark Phoebe ring, a phantom structure that paints the face of Iapetus, and we confronted the sobering reality of ring rain, a constant downpour that is actively draining this magnificent structure into Saturn's clouds. From the thermal paradox of a cool sunlit side and a warm shaded side to the intricate electromagnetic interactions that shape and shield, and from the vibrant E-ring, a plume from the potentially habitable ocean of Enceladus, to the color gradients and time-variable changes that prove these are not static rings but a living system, every mystery has peeled back a layer, revealing not simplicity, but staggering complexity. This is the ultimate takeaway. Saturn's rings are not a beautiful but passive ornament. They are a dynamic, open-air laboratory for physics. Within those trillions of orbiting ice particles, we can study the fundamental processes that govern our universe, the delicate balance of gravity and orbital motion at the Roche limit, the chaotic beauty of granular materials, the unseen forces of plasma and magnetism, and even the conditions that could lead to the emergence of life. They are a teaching moment on a planetary scale, showing us that the cosmos is not a still life but a vibrant, evolving, and deeply interconnected place. The next time you have the chance to look up at that tiny, golden jewel in the night sky, know that you are not just seeing a planet. You are witnessing a grand cosmic experiment, a temporary masterpiece of ice and rock, where forces we are still striving to comprehend dance in a delicate balance between creation and destruction. And the story is far from over. Future missions armed with even more sophisticated tools will undoubtedly venture back to this ringed world, ready to read the next chapter and uncover the secrets that still lie hidden within those glorious, gleaming bands.